Thank you, Emily. Good morning, everyone. Thanks for being here early to hear about brown dwarfs. And it's a pleasure to speak at the Sagan workshop. When I was a junior postdoc, I once gave a plenary talk with Carl Sagan sitting right in the front row where Mike Line is. And I was so nervous, my my hand was shaking back and forth and the pointer was bouncing all around the screen. So hopefully it'll be a little bit better today. So why do we care? Why do we care about brown dwarfs? From the point of view of exoplanet atmospheres. So for giant atmospheres, they're relevant because these are hydrogen helium objects. They have masses below the hydrogen fusion limit. So this is the effective temperature versus age for these guys. And you can see they just radiate and there's the pointer. They radiate and just cool off over time, unless you're above the hydrogen burning minimum mass, in which case you turn into a M star and just fuse for a long time. So the range of atmospheres that we're looking at is this a few hundred Kelvin to a couple of thousand Kelvin range, which is right in the same range as the hot Jupiters and many of the directly imaged young planets. And the atmospheric processes of brown dwarfs are all very similar to those we see in the solar system atmospheres. Okay, and it's easy, and also brown dwarfs are easier to observe and obtain spectra of, and they provide a learning and testing ground for the exoplanets. And so pretty much anything you hear about exoplanet atmospheres, it was seen or it happened or understood first in the context of brown dwarfs. And it's not going forward. There we go. So why am I the one, why am I talking to you about this? I've been studying brown dwarfs for a long time. My first paper I ever wrote was a co-author on was in 1986, which was about brown dwarfs, and it was before the first discovery. My first exoplanet paper was in 1999, so I've seen both fields mature along somewhat different tracks, and I think I have an idea of what some of the lessons learned from the various fields are. So if we think about solar system science, which we're going to hear about from Lee, and of course exoplanets we're all here for, and brown dwarf science, one of the really important areas of overlap of all three of these is atmospheric processes. And this includes things like energy transport, the chemistry, the clouds, the photochemistry, the dynamics, and more are all things that are relevant to all of these fields. And it's a great opportunity to learn from each other, to learn from what we've understood in all these different contexts. And the atmosphere is so important because it absorbs energy from the incident starlight or sunlight, and as well as it's transporting the energy from the interior as objects cool off over time is being transported through the atmosphere. So the atmosphere is regulating the temperature and the energy budget of the entire planet. And of course, for most of the things we study, the photons come through the atmospheres. The atmosphere is regulating everything we can learn about the planet in that sense. And so brown dwarfs are great because they test our understanding of atmospheric processes and connect the solar system and extrasolar giant planets. And one theme of my talk today is that our goal is to understand the processes, what's happening in these atmospheres. It's not solely to retrieve a number. We're going to hear about retrievals, and that's great. But the value of these things is to connect properties we can see to the underlying physical processes, which is where we want to be going. And so in my talk today, I'm going to give a very short reminder for you of what we know about brown dwarfs, with properties of brown dwarfs. And then I'm going to focus on lessons learned for three different categories of things: clouds, hazes, and chemistry. I'm going to talk about rainout chemistry and disequilibrium chemistry, and then give some concluding thoughts and advice. And all of these things are the kinds of things that we can see in our own solar system. So let's just start off by placing these atmospheres in context. Here's a log temperature scale on the bottom, pressure, atmospheric profiles, pressure, the altitude going up. So here's what the sun looks like. Here's an M dwarf, cooler, an L dwarf, still cooler, a T dwarf here, and then Jupiter. And if you plot condensation curves, which is the temperature pressure conditions where molecules in the atmosphere form condensates, some of the more important ones are shown here. And so you'll notice, like for the sun doesn't have clouds, M dwarf doesn't have clouds, but as you get cooler, the atmosphere starts existing in this temperature pressure space where you get condensates. And so fundamentally, a fundamental property of brown dwarfs is that they're cloudy. They've got stuff in the atmosphere. There's a range of objects called T-dwarfs that are mostly cloud-free. And then we get down to Jupiter where we have water clouds and ammonia clouds. Also, as you heard from Julie Moses, I think on Monday, there's important differences in the chemistry as you go cooler. One of the big ones is where carbon is found. And at the warmer atmospheres, carbon is found in carbon monoxide. And in the cooler atmospheres under equilibrium, methane is more abundant than carbon monoxide because the carbon is found in methane. I'll come back to that. And so all of these things combined together give us a spectral sequence. And this is a figure from Mike Cushing, which we've been evolving over about 15 years as the data has gotten better and better. And now we used to have models here, and now this is real JWST data of a 450 Kelvin brown dwarf. But you can see as you go cooler, the molecular features get deeper and deeper all the way down to Jupiter. And we just see this whole host of features. This portion of Jupiter's spectrum is reflected light, and then we see thermal emission beyond about 4 microns. And just to kind of make the point, this is a spectrum of Jupiter in black and a fairly new JWST spectrum of one of the coldest brown dwarfs, WISE 2209, which has an effective temperature of around 370 Kelvin, which is like an oven on bake, just about. So let me go back. And so there's lots of all kinds of interesting overlaps, similar features, and then very important and interesting differences. So let's get right into the lesson learned. Let's talk about the most difficult thing, which is clouds. And as I said, clouds are really the defining factor of the atmospheres of brown dwarfs and substellar objects. And this is a color magnitude diagram where this is J band, their things are brighter towards the top and is a little cut off on the bottom, J minus K, infrared color. And the thing about brown dwarfs, as you look at cooler and cooler objects, is they get redder and redder and redder. But then there's this funny, as you go even cooler, there's this funny turn to the blue, and then things get fainter over here on the blue side. And what's happening is in the realm of the L dwarfs, which are the like 1,000 to 2,000 Kelvin brown dwarfs, we're getting more and more and more clouds. So the objects are getting redder. And then something happens down here where we lose the clouds and we get more of a cloudless atmosphere. Now, and this is the kind of thing we want to understand is what's causing this trend. And it's hard because clouds are intrinsically a 3D process, but we have to start somewhere. We start with like 1D models. And the kinds of things we need from the models in order to model spectra and the characteristics of these things is the particle sizes, the composition, where they are vertically and horizontally in the atmosphere, and what's causing variability. Lots of brown dwarfs are showing variability with time. And so how do the clouds feed into that? So it's kind of easy to say, oh yeah, there's clouds, but it's very hard to say exactly what's going on with these clouds. What are these clouds made of? Let me show you kind of a cartoon picture of what clouds do for us. And imagine here we have a little piece of a spectrum. And in the middle, I always think of it as we're looking down into the atmosphere to see different levels in the atmosphere. I was just at Lake Tahoe and it's so clear, right? You can see really deep. So this is like the Lake Tahoe region where you're seeing really deep. And when you're seeing deep, the atmosphere is hotter. Here's a little temperature pressure profile to orient you on the side. And so you get more flux. So maybe this is a region with low water opacity. And then over here on the shoulders are regions where water absorbs more strongly. And it's like a cloudy lake. You can't see as deep. And so we get less flux because you're seeing flux from where it's not as warm. But now let's imagine we put a cloud in here. And what that cloud does is limit how deep we can see. So now here in the region that used to be really clear, we can't see so deep. And so we're seeing less warm air. And so that shaves off the peak in this flux. Meanwhile, because you have to balance the energy flux out of the object, the rest of the atmosphere warms up a little bit. And so you get more flux. It gets brighter here in the areas where water absorbs strongly. And so that's very similar to what we look at this 5-micron image of Saturn, um, where the dark regions are regions where we're looking down at clouds, and the clear, brighter regions is where there's fewer clouds and we can see deeper into the atmosphere at the hotter layers. So if we want to understand this and model this, we have to have some picture of what are these clouds that are so important? What are these clouds doing? And there's different modeling schools. Peter Cao is going to be talking about models later in the meeting. And I like to think of it, there's different flavors of models. One is what I call here on the top left, the top-down models, like the Christian Helling's group and the Karma models. And the basic idea is that the model sprinkles condensate seeds at the top of the atmosphere, which then fall down and grow through the atmosphere, and you end up with an equilibrium state of the cloud models. Then that tries to model all the microphysics and the details of what's going on. There's also fixed models, which are sort of like that cartoon where I just slid in a slab of clouds. There's our own cloud model, which is sort of, I think of the bottom up. It starts with a parcel rising up in the atmosphere and looks at where things condense and what happens to them and how they grow. That's the Ackerman and Marley model, or there's now the open source version called Virga you'll be hearing about, and also ExoRim. And then finally, there's pure chemical equilibrium models like the Phoenix Dusty models. So if we have a model, then we can then start to say, okay, let's see if we can understand these atmospheres. I'm going to show you a few comparisons to give you an idea of how this stuff works. So here in the black is a spectrum from 1 to 10 microns. In these figures, the mid-infrared spectra is from the Spitzer IRS instrument. And the inset is a little color magnitude diagram like I was showing you, and here's where this particular object is. So we can use our models and do a fit and derive some parameters, and it's a decent, for brown dwarfs, this is a decent quality fit. But the interesting thing is this includes clouds. If I show you exactly the same model, but I sweep out the clouds, it's just what I showed you. At the peaks, we see deeper now without the clouds, we get more flux, and then it's colder at the top of the atmosphere here. So within the water bands, we get less flux. And so the dynamic range is larger. Now, if I ask you, how do you know there's clouds here? You really can't point to any spectral feature and say, oh, there's the cloud feature. But instead, it's this overall attenuation of the model that tells you there has to be clouds. If we go to something colder, now 1700 Kelvin, it's the same thing. Red is cloudy, blue is cloudless. Clearly, this object has clouds. We go even colder. Now we're down to 1400 Kelvin. We're at the bottom right of the color magnitude diagram. And the models, it's harder because it's so cloudy, it's harder to fit these, but you can see clearly the blue model doesn't work at all. But the interesting thing is, okay, this is 1400 Kelvin. Let's go 100 Kelvin colder. And this is a cloudless model. So in just 100 Kelvin, something's happened to our clouds. And we still don't understand exactly what this is. If I put up a cloudy model, it's in red, it doesn't look anything like the data. So one of the big mysteries of brown dwarfs is, where did the clouds go at this L to T transition? So the broadband signature of the clouds is unmistakable, there has to be there. But pinning your finger on it is hard. So the silicate absorption features, we can kind of see it in the IRS data. It's this little curve here, which arises from the absorption of magnesium silicates in the atmosphere. This is going to get easier with JWST, and there's going to be a lot more data. In fact, the VHS 1256b paper from Brittany Miles is just amazing. And here is that same silicate feature. So now we're seeing this with JWST, and hopefully we'll be able to start identifying individual species. So the silicate spectral feature we do see, so we know that there's clouds from the broadband. We're starting to see the silicate feature. This is a retrieval from Ben Burningham's group. But the interesting thing is the retrieval likes to put in the silicate, instantite clouds that you expect, but also quartz clouds, which you do not expect. seem to be present in the data. So what's causing that? Is it related to the chemistry of the atmosphere? That's the kind of thing we need to understand. I'll also say that it helps you, if you're interested in this stuff, to go off and learn a little mineralogy. As an undergrad, I learned mineralogy about 200 yards from this spot, and I never thought it would help me in astronomy, but it does in the end help understand the context of these astronomical objects, which is interesting. But there's a lot to learn and to connect the mineralogy to what we're seeing. There's lots of room for improvement in cloud models. But it's important, remember, clouds are really hard, even for the Earth models. It's very, very difficult. And so we shouldn't ever expect a simple 1D cloud model to be very good. We need better models, but the advice is, regardless of which model you use, you want to aim for understanding the physical processes, not just reporting, oh, I turned this knob and matched the data. It's why am I getting these numbers, or what's the trend? And that's the important thing. And with brown dwarfs, we're still not there. But for the next 20 years of exoplanet atmospheres, that's really one thing we really have to figure out, is doing the clouds better. Let me give you a cautionary tale, though, about clouds. The very first brown dwarf was Lisa 229b. It was discovered in the mid-90s by a group right here at Caltech. This is the discovery images, from Palomar and from HST. It's about a 60 Jupiter mass object, about 900 Kelvin. And we published one of the first model papers to try to explain this. This is the model fit that we showed in our paper. But the interesting thing is our plot stops at a micron here, which was a little bit, and part of the reason was, if we went shorter than a micron, the models were vastly different than the data, like off by a factor of 100. And so Caitlin Griffith and I were talking about this, and it both reminded us of Titan, where there's all this haze. And Gliese 229b is a companion object. It does get some UV irradiation. And we thought maybe there's this haze or small particles in this thing's atmosphere. And sure enough, if you put in a model of organic hazes and you tune it a little bit, you can fit the data beautifully. So we wrote a paper in Science, here we are on it, called The Dusty Atmosphere of Brown Dwarf 229b. And right here in the abstracts is organic composition. These hazes have an organic composition characteristics of aerosols and planetary atmospheres. So that's great. We've discovered hazes in this object. The only problem is it's wrong. We were leaving out sodium and potassium, gaseous sodium and potassium opacity from our models. And it turns out in these objects, they're very highly pressure brought, and it's a really important opacity source. And that's the reason the models are off by orders of magnitude if you don't include that. So that's kind of a cautionary tale. Chaz just told me the JWST data are much better than the theorists. And so this is it's always been true. And this is an example of that. And but we just have to be careful, because this is, transit spectra of some hot Jupiter, lots of hot Jupiters. A lot of times there's this turn up to the blue, and it's commonly attributed to small particles in the atmosphere, kind of hazes. And whenever I see that, this is probably right, but whenever I think of it, I think of the brown dwarf case, where we thought for sure we'd seen small particle hazes, and we were wrong. So just be careful. The lesson learned is just be careful of attributing model misfits to some mysterious, cloud process. It may not be the case. Okay, so that's kind of the effect of clouds on radiative transfer, but there's also the effect of clouds on chemistry. And there's something called rainout I'd like to tell you about. That's also a lesson learned from brown dwarfs. This is a figure, kind of a cartoon stack of clouds in Jupiter's atmosphere from Katharina Lotters. And if you look at the chemistry, at high temperatures, the refractory minerals condense, and then we have iron as we go up, and eventually we get the water clouds and ammonia clouds that we see in Jupiter's atmosphere. But a question when we do the chemistry is, let's say we've got air, up in here. Does this air know about this iron cloud below it? Or how much does the iron get distributed? And we can actually tell that, because the iron forms around 1700, 1800 Kelvin, but down around 600 or 700 Kelvin, iron reacts with hydrogen sulfide to make FeS. And so if the air up here was in contact with the iron from this iron cloud, like imagine the iron cloud is mixed way up or there's really strong convection or something, it would pull out the hydrogen sulfide from the atmosphere and we wouldn't see it. But in fact, we do see H2S in Jupiter's atmosphere. So we don't. The iron is not talking to the H2S. And so when we do the chemistry, we have to not just do pure equilibrium chemistry, we have to account for the fact the iron is removed from the atmosphere. And we can do the same kind of test for brown dwarfs, the same kind of question, except for the these clouds. These are some of the trace clouds that show up in the cooler brown dwarfs. I've kind of glazed over, but they're there, but like potassium chloride. And these species, and like the sodium and potassium, that we see in the atmosphere, if the sodium and potassium in the atmosphere talks, if it talks to the corundum, which is Al2O3, then it forms, the chemistry tells you it would form albite, which is this compound here. And so we can test this by saying, when does the gaseous sodium and potassium disappear from the atmosphere? Does it disappear at high temperatures, which is what you'd expect if the gas was talking to the cloud, that refractory cloud, or does it disappear at low temperatures to make the sodium chloride or potassium chloride cloud here? And Mike Line's student, again, his first name, Zaleski, Joe Zaleski, did this study. And so here's what you would predict in pure chemical equilibrium. This is what you would predict for the rainout chemistry. And the gaseous sodium potassium follows from the retrieval studies, follows this rainout curve. So again, that tells you that these species are being sequestered away in finite clouds very deep in the atmosphere. We may not see the clouds, but we can see the fingerprint of the clouds by looking at the abundances. Just like with H2S at Jupiter, the sodium with potassium tells us about deep clouds we can't see. And so I really like this as an example of the kind of understanding we should be aiming for, looking for trends and the processes, and not just thinking, okay, this brown dwarf X has this abundance and then moving on, but it's rather putting it in context to teach us something about the atmosphere. It's also a great example, I think, of the brown dwarf exoplanet planetary science connection, where these are things that work in all three atmospheres. So let me end up on disequilibrium chemistry. I know Julie talked about this, so I'll just briefly remind you that deep in the atmosphere, say where it's warm, we expect the carbon to be in the form of carbon monoxide. Cooler, this is in this particular plot, cooler up is towards the left. Cooler in the lower temperatures in the atmosphere higher up, chemical equilibrium predicts the carbon's going to all go to methane, and there would be hardly any CO in a cool brown dwarf. But in fact, there's mixing in the atmosphere, and if the mixing timescales are faster than the chemical equilibrium timescales, you can dredge up this carbon monoxide, and so you can see it. And it can be a couple orders of magnitude more CO than you expect. And so this is something that a lot of exoplanet papers and brown dwarf papers, like, oh, look, planet X or brown dwarf Y has disequilibrium chemistry. But I have to tell you, it's not that interesting by itself, okay? This is a little bit of, I don't want to hurt anybody's feelings, but we've known about this since the 1970s, okay? People worked this out in Jupiter's atmosphere, and some of the early pioneers understood this right away from, John Lewis in the 1970s. And as soon as the first brown dwarf was discovered, Fegley and Lauders predicted that brown dwarfs would show disequilibrium chemistry. Knoll et al. Found disequilibrium chemistry just a year later. So we understand that this happens. And so the interesting thing is not that it's there, but the interesting thing is the trends. And so the lesson learned is we don't need any more simple examples. Instead, let's try to do things like Brittany Miles did recently, and looking at a lot of brown dwarfs, looking at the carbon monoxide abundances, and then mapping that back into the strength of mixing in the atmosphere. And she produced a plot that looks something like this. This is brown dwarfs at different effective temperatures. And KZZ is this measure of how strong the atmospheric mixing is. And at the warmer brown dwarfs, it looks stronger, and then it kind of drops off, and then it gets really strong. Look at Jupiter way up here. And so there's this interesting pattern that we need to understand that's telling us about what's going on in the atmosphere. So again, what's interesting, the lesson from brown dwarfs is it's the trend, it's the processes in the atmosphere. This is what we really want to get, you really want to get to, and I encourage you to think about. So in summary, brown dwarfs are interesting. Most all of the exoplanet atmospheric topics were studied in brown dwarfs first. It's worthwhile to take the time to learn a little bit about the literature. Some specific lessons is clouds are hard. We need better models. Don't focus on model parameters too much just yet. Don't blame clouds for every mismatch you see, and take rainout chemistry seriously. And I think it's time to move on with disequilibrium chemistry and try to get more at fundamental processes. And so let's focus on understanding the trends and what's happening in these atmospheres. And I think that's what's exciting. So thank you.
Okay, thank you very much, Mark. That was fantastic. Do we have any questions from the audience?
Hi, my name is Mara Banjikji. I'm a grad student at ASU studying brown dwarfs. So I just want to say thank you for representing a very awesome field and for the great talk. My question is, you say we need to focus on understanding the trends in physical processes. Do you have any suggestions for how we can do this for brown dwarfs and also, I guess, exoplanets too?
Well, I mean, it's hard. And so you have to kind of learn individually about the processes and, ask yourself, what is this number, telling me? There's a lot of like, oh, let's get the C to O ratio, and that tells us about formation. And then that's interesting, but it's also, we don't always have to go to formation, right? We can go to, what does that tell us about mixing in the atmosphere? Or what does that tell us about these other, processes? And so I guess we need better models. We need more accessible models. Like this afternoon, you'll all be seeing some, opportunities to learn about these tools. And so I just understand what these tools are doing and understand how the numbers relate to the processes. And what process aren't we thinking of yet?
We have one online question asked, once a gas species is removed via rain out, is it still possible for it to somehow go back to its gas phase? If not, will the said species eventually deplete over time without any means of enrichment? Sorry. So it asks, once a gas species is removed via rain out, is it still possible for it to somehow go back to its gas phase? If not, will the said species eventually deplete over time without any means of enrichment?
Yeah, no, thank you. So if something's formed into a cloud, there's the vapor, it's called the vapor pressure equilibrium. There's still a little bit above the cloud, but as it gets colder and colder, more and more of the species is going to be condensed, and eventually you lose all of it. So unless there's some kind of mixing process that's bringing it up, it's not, the atmosphere has sort of dried out, if you think of it in the water context, and it's not found above there. But like in the Earth's atmosphere, there's these super strong convective columns in the tropics that can insert water up into the stratosphere. And so if there's a physical process that can do that, then yes, it can do it. You can get some of the condensed species up higher, but there has to be something going on to do that.
Hi, here. One question about the two different ways of modeling clouds that you mentioned, like there is a Christian Helling approach and your approach. I was wondering if the spectra that you found with the two different models are similar or there are differences in the predictions.
Yeah, I mean, that's a great question. The question, are there differences in what the models predict? And the cloud modeling is still not far enough along. I think, for example, the microphysical models take a long time to converge. And so we don't have model grids of like thousands of models for the microphysical case. So we can really say, oh, we know there's some fingerprint that we see. But as the models get faster and we get better, that's definitely something that we need to look for. It's like, what's the fingerprint of the microphysics versus the other approaches?
Yeah, Mark. I mean, with the brown dwarfs, we presumably have objects that formed with cloud or disk fragmentation. With the giant planets at large separation, we haven't a clue. But when we come to the solar system, the planets formed presumably by core accretion up. If I now take a spectrum of each, is there anything at all that you would say tells you about these diametrically different formation mechanisms?
Yeah, so the core accretion certainly gives you, if you then have a late stage, continuous accretion to the atmosphere after you've made it from the solids. And so you certainly see, as we see with the solar system giants, all of them are enhanced, as you know, in heavy elements. And then you can start to make arguments about where you're accreting from and what the carbon and oxygen abundances are of the solids you're accreting, or even the isotopic abundances. So yes, you can start to connect it, but I think I don't think there's a slam dunk for core accretion or not, but I think there's, again, maybe in the trends, we'll start to see those fingerprints.